Hi guys, in this video I'm going to teach you how to deal with a circular motion and forces. So in this problem we're going to take a look of a motion of a car on a banked curve. So let's look at this example. A highway curves are often banked to reduce a vehicle reliance when negotiating the turn. On a banked curve, so you have to know that we are dealing with a banked curve. There's a centripetal component of a normal force acting on a vehicle when the angle and the speed are such that the friction plays no role in a vehicle. So that means there's no friction. Vehicle's motion in the curve. The nature of the road surface is immaterial, and thus the posted speed limit applies in both wet and dry weather. Suppose the posted limit speed is this on a curve of a radius 180. At what angle theta to the horizontal should the curve be banked so that reliance on a friction is not necessary? So you have to know that when a car is moving on a curve, there are two things that make a car to turn. It's either the frictional force or the normal force. So the normal force takes place where the curve was banked. So if the curve is not banked, it's just like this. What makes a car to turn is a frictional force. Remember that if you are looking to the side view of a car on a banked curve, not a banked curve, you are going to see something like this. But if you are looking to the side, this is a side view, then what about if you are looking to the top view? So the top view is going to be something like this. You're going to see something like this. So you just see a car here. So a car is moving on a cycle actually. So that means this is a side view when you are standing here. When you are here, you will see something like that. But when you are on the side view, it's like this. This is a top view, that's a side view. So this is a top view. So actually you have to understand what's happening when you're looking to the car on a side view and then when you're looking to the car on a top view. On a side view, you just see the side of the car, not only. You don't realize that the car actually is turning, but on a top view is where you're going to see that the car actually is turning along the curve. So what makes the car to not slip off the road is the frictional force. So that means the frictional force is pulling this car to the other side. That's why the acceleration is going to point on the other side. So if the acceleration is going to point in this direction, that means we are going to have a centripetal acceleration. But on a side view, you can't see that centripetal acceleration. So it's what makes the car to turn. So if you draw the free body diagram here, you are going to have something like this. You are going to have a normal force and then the frictional force which is pulling off the car not slip off the road. So that means the frictional force is going to be in that direction. It's the one that makes a car to turn actually. And then you are going to have a Fg weight, and then this is going to be the frictional force, and then this is going to be the normal force, F normal. So let's look at the banked curve, because remember this, I was just showing you an example of a plane curve that's not banked. So let's look on a banked curve. So a banked curve is going to be like this. Remember that the curve is banked, it's not plane. So that means when you look at the top view, you still see the very same thing. The curve doesn't change. You still see this. Let me draw another one. You still see something like this. So when you see something like this, a car, it will be here. This is a top view. But the side view on a banked curve, if the curve is banked now, it's going to be like this. You are going to see something like this. So the car, it's here, and then you are standing by here. Then that means you are here. So you see something like this, while here you just see top view is something like this, and then side view is something like that. Then so according to the problem that you are given, there are describing this situation where they're talking about the banked curve. So they're talking about this kind of curve, not a plain curve. So that means we are going to consider this type of motion, a circular motion of a car on a banked curve. So remember that, as I told you, what makes a car to not slip off the road is a frictional force on a plane curve. But on a banked curve, because the slope is like that, what makes this car to not go to that side is because the slope is banked. So that means it's going to be one of the component of the normal force. Remember that that component has to point in this direction to the centripetal acceleration. So if that force has to point in that direction, that means makes a car not to slip off the curve, stay on a curve, and then at the same time turn. So that component of the normal force has a limit. That's why always on the curves they post the speed limit, so that to tell you that don't exceed this speed or don't go below the speed. You have to move with that speed so your car can stay on the road. But if you change the speed now, maybe you are moving with a speed that is higher than that, a car can slip off the road. Then here we are considering the case where the car doesn't slip, because we are told what is the minimum speed that can keep the car on the road. So let's consider this one. Let's draw the free body diagram of this and see what's happening here. So if you decide to draw the free body diagram of this, let's draw the reference. So our reference is going to be like that, and then let's consider the object of focus, which is the car. So that car has a normal force which points this way. So this the normal force. Also has a weight which is downwards, and then only two forces are acting on a car, but the car doesn't slip off. Why? Because this normal force doesn't point upwards. Remember, if the normal force points upwards, we will have no force going that direction and then no force going that direction, then the car will slip off. So because that normal force doesn't point upwards, point on this direction, that means I'm going to have two components of the normal force. So those components is gonna be this component here. So this is a F normal X, and then here I will have another component. I'm going to call this F normal Y, and then this is a F normal. So that F normal is divided into two components, the X component and the Y component. Then the question asked us to, at what angle theta to the horizontal should the curve be banked so that the reliance on a friction is not necessary? Remember that if the curve, the angle increases, therefore the car is gonna slip off down. And then if the angle is decreased, then the car is gonna slip off the road. So that means this angle should be at a certain limit where it keeps this car not slipping out of the road and then not slipping down, just stay on the road. So we want to calculate that angle that will make this car to stay on the road. So we are going to use all of this. So what I see here up so far now is that I have two things. This F normal Y component, this angle is the same as that. These two angles, no, these two forces are the same. So since these two forces are the same, that means there is no acceleration on the Y direction. Why? Because the F net is equal to 0. This normal component and then this weight, they add up to 0, and then I have no acceleration on the Y direction. But look at this now. You have F and X, which is a component of the normal force on the X direction. So this one, it has no a pair of force that is going to cancel it. So that's why I have acceleration. I have my acceleration, X acceleration, pointing in this direction. So the reason the acceleration is pointing in this direction is because this force is the one that makes the car to turn, and then at the same time points in this direction. So my F net actually of the entire of this is gonna point in this direction. So my f(a)x acceleration, I have only acceleration of x component acceleration pointing in this direction. Remember that this is a x, then that's a y. So my acceleration point in the x direction. So what's gonna happen here is that this acceleration at the same time is called the centripetal acceleration. Remember that is pointing to the axis of rotation. So here we have an axis of rotation, and then we are told what is the radius of this. So we are told that from here to the center of the car radius, we have that radius, it's 180 meters. So here, from here to there, that's 180 meters. Then what you are left with now is to calculate the angle. So since I know that the y component forces cancel each other, so I'm going to say the sum of Fy is equals to 0, and then the sum of Fx is equals to mass times acceleration. So this acceleration, remember that I told you that is at the same time is a centripetal acceleration because it's pointing to the axis of rotation. So here we have this equation, sum of the Fx is equals to m, which is the mass of the car, multiplied by the acceleration to the x direction. So now I should calculate my angle theta. So let me rub this here so I can have a space of doing that. So remember, I have to define this force here in terms of theta. So remember that on a curve like this, if I can have a point here, if I can have a point here, and then I will have my normal as this. So the normal makes 90 degrees with the surface, and then at the same time I will have this. So this is going to be my F, is going to be this force, my Fn of x. So remember, if I can take this sketch out here, this is my weight, and then that's my Fny. So if I can take this sketch here out, I'm gonna have something like this. I'll have something like this. So if I take this out, that means I have here, remember that I have this as the f of nx, and then this point is here, and then I have my f of ny, and then remember that I still have my surface here, and then I have this angle here. I have this angle here as theta. So that means this angle is equals to that because these two lines are parallel. So if these two lines are parallel, also this angle here is theta. And then after that I have the y component, no, the normal force. So the normal force make it 90 degrees with a surface. So remember, if I have a theta here, also there is theta because of the parallel lines. And then after getting this angle, that is theta, remember that I have a 90 degrees. So this angle here, it's 90 minus theta. So if this angle here, it's 90 minus theta. So what about this angle here? Since this is 90 minus theta, and then I have another 90 degrees here. This is the 90 degrees. So here I have 90 minus theta. So therefore this angle here is also going to be theta. So this angle and that angle and that angle are equal. So this is the only way strategy of finding the f and y in terms of theta. So that means I have my theta now here. So that means this force here is the same as this force here. So these two forces are the same. So what's gonna happen is like I'm going to have something like this. If I can draw the sketch, this is going to be my f and y, and then this is going to be my f and x, and then this is going to be my normal. F normal, and then after that I will have a weight. That's my sketch. So if I have something like this, and then I told you here is going to be theta taken from here, this is theta, and then you have something like that. So if I have theta, I want to write this f and y in terms of theta, and then this f and x in terms of theta. So therefore I will have something like this. F and y is going to be, remember that's on the adjacent side, so it's going to be cos. So it's going to be f n times cos of theta. So if that's f n y is equals to f n times cos theta, so what's going to be f n x? So the f n x is going to be f n times sine of theta. So you have something like this. The normal component, the normal force of y component is equals to the normal force multiplied by the cos of theta, and then the fn x, which is the x component, is equals to the fn multiplied by sine theta. And then after doing that, that means you can come here and then substitute your forces, then get the angle theta. So since I have something like that, so I got this from the sketch, then the next step I'm going to substitute this equation on my equations there. So I'm going to have something like this. Remember that this is a f y, so we're looking to the y component, which is this f and y, and then weight. So that means these two forces are equal, so that's why, and then they're pointing into the opposite direction. I can write something like this: f and y minus fg, which is a weight, is equals to 0. They add up to 0. Remember, they're equal. We don't have a y component acceleration, and then that means this fn, I have it here, is the same as fn times cos of theta, and then it's equals to mg. So now I'm going to make my fn as the subject of the formula. So if I make fn as the subject of the formula, I'm going to have something like this: fn is equals to mg divided by cosine theta. So that's fn is equals to the mg cosine of theta. Then after that, I'm going to calculate my x component forces. So the f component forces in this way, they are not 0. They don't add up to 0. That means the acceleration is not 0, because this force here is just alone, doesn't have another force that can cancel it out. So therefore I'm going to have something like this. For the f component, this one here, I'm going to have something like this. Is a f nx is equals to m times a centripetal acceleration, because that acceleration, as I showed you, that is pointing in this direction, where at the same time it's the centripetal acceleration. Then the fnx is this one, I have it, is a fn multiplied by sine of theta is equals to mass times centripetal acceleration. We know that the centripetal acceleration is equals to the velocity squared divided by the r. So if I'm going to substitute this centripetal acceleration as a v squared over r, so if you substitute that by the v squared over r, that means you are going to have something like this. So remember that I have a fn here. I have my fn. What is the normal force? So the normal force is this. So I can call this as equation 1. Therefore, I can substitute that fn to here, so that I will find my theta. Then the fn, that means that if I substitute it here, it's going to be mg, and then cosine of theta multiplied by, this is divided by, multiplied by the sine of theta is equals to I think I'm going to run out of space, and then is equals to mass times v squared over r squared. R, not r squared, sorry. So what I see here is that means this mass here can cancel out that mass. So the mass cancel out the mass. Then remember that sine theta divided by cos theta is equals to tan theta. Then I will have something like this. G times tan of theta is equals to v squared over r. So after that I can divide both sides by g. Therefore this equation can come here, and then I will have something like this. Tan of theta is equals to v squared over rg. Then if I want to calculate the theta now, that means I have to find the arc of tan. And then therefore from this from that means I will have something like this, and then I will find my theta, and then theta is equals to tan second function v squared over rg. Then that's my theta. Therefore theta is equals to, remember that I'm given what is the v here is 100 km per hour. So what you have to do is just to convert that 100 km per hour to meter per second, because a velocity must be in meter per second. And then to convert that one, it's simple. Just do this, convert that 100 meter per second to, so to convert that meter per second to kilometer per hour to meter per second, you're going to say v is equals to 100 divided by 3.6. So this v is equals to 27.78 meter per second. So if you got that, therefore you can go and substitute, because we are told that our r is equals to 180 meter. So the r is on the right units, and then g, we know that g is equals to 9.8. Then if you substitute this to that equation, therefore you are going to have a tan of -1, and then what is v? V, you have that 27.78 squared, then divide by r, which is 180, then times g, which is 9.8. Then when you punch that on a calculator,